Hello and welcome. In this talk, I'll be discussing an experiment and through that a field where applying classical methods of psychology for learning more about high-level perception would be very useful, but that is something that we are rarely seeing yet. And the topic is lamps on cars with obvious safety implications. And in this field, we've seen quite a bit of change lately due to developments in LED technology and light guides. And we are seeing more and more prototypes and concept cars which display novel lamp configurations like the ones here or these. They usually include the illumination of the grille area and also light guides along the sideline of the car or around the windows, etc. And these layouts are not legal yet in most countries, but seeing the amount of emphasis that the car industry puts onto developing them, it appears likely that regulations are going to change. Here are some patents describing signaling functionalities for such new lamp configurations, aside from the obvious design and branding role for them. But so the question arises whether they could be used to increase traffic safety and if they could be implemented in a way which had perceptual benefits. When it comes to pedestrians and cyclists, there have been a couple of studies to show that highlighting the most prototypical aspects of the object can lead to an increase in the object's visibility. So in terms of a pedestrian, the feet and the lower limbs carry cues of biological motion, which are very informative and also perceptually salient. And so highlighting these, as opposed to any other parts of the body, has perceptual benefits. Similarly for a bicycle, even though the movement of its parts are not biological, but still some parts, like the wheels, the legs, and the pedals, the things which turn, they carry more information than the rest of the vehicle or the cyclist. And so this knowledge is not yet really incorporated into everyday life. Most cyclists tend to believe in vests and electric lights, and also regulations focus on these primarily, but we know that these are not the most informative and not the most useful locations to highlight. And then moving one category up from here, a motorbike does not really have moving parts to show. Maybe the wheels could be utilized somehow, but so basically it's a static frame. However, if the prototypical aspects of it are highlighted, that comes with visibility advantages. And so all this leads basically to object perception. So if the same amount of light is presented in one location, say the lamps of a bicycle, that carries very little information. If there's just a point like light source somewhere that does not have information regarding depth or distance, and through that it also doesn't convey information about trajectory, velocity, size, identity, basically anything else, but the fact that there is something there in a certain direction, right? And so the idea with object perception eventually is to make objects appear more similar during the nighttime to how they look in daylight. And obviously then the conclusion is that the best solution would be to wrap or paint a car with a material that is luminescent all over, and such technology exists. Here's an example by Nissan. However, it has some drawbacks. For instance, it is prohibitively expensive right now, and also it would not differentiate between, for instance, a parked car and a car in traffic. And so most development seems to be going towards LEDs and using light guides to accentuate certain parts of the chassis. Here's an example of masking and how such extra lights could be utilized. So this masking is about confusion of identity. Basically, two tail lamps can be integrated the wrong way, one belonging to a truck, the other to a motorbike. And actually, these masking scenarios can be avoided with the retroreflective tape patterns, which are also mandated in many countries, like here in this image. And since these have been used, there's also data to show that they actually do have perceptual benefits in traffic. Here's another masking scenario. There are two images here which are identical in terms of what they present. So both on the left and the right sides, you see one car and one bicycle. However, in the left side image, the unlit cyclist is dark, the background is dark, and the contrast is huge between the main glare source, the headlight, and the rest of the scene, which is all dark. And therefore, there's not enough contrast between the cyclist and the background to see its silhouettes. However, when the car displays a large luminous surface, against this surface, even the dark silhouette of the bicyclist can be perceptually interpreted and perceived. And so several such mechanisms eventually lead to the broad concept of crowding, which means a hindrance in seeing something peripherally when that object is surrounded by other objects, which we can call flankers or distractors. And here there are two concepts to note. One is integration. So the hindrance in seeing our main object comes through integration between the parts of this object and the parts of the other objects around it, right? And the other one is similarity. This integration is going to happen more likely if parts are more similar. And so note here that in order to perceive a car as a car in the darkness, only based on its two headlights, already includes or necessitates an integration, a correct integration of these two headlamps, or the light of these two lamps. And so when the scene contains other lamps, as at nighttime it tends to, there's a bigger chance of improper integration with other lamps. And so here, how we see it in the classical crowding paradigm, say the participant would be fixating on this point, and at some angle from this point, so peripherally, there are three characters presented. And the task is to tell what character is in the center. And in this example, crowding is more likely because the flanking characters, as well as the target, consists of vertical and horizontal lines. So crowding would be less likely, for instance, if the flanking characters are round characters. And so to test in a first step, in a simplistic way, whether such contour lamps, as I call them, could have perceptual benefits in terms of crowding and masking mechanisms, isolated from any contextual cues or any other aspects of the visual side of being in traffic, we carried out a simple search paradigm where a target motorbike image had to be found while it was surrounded by cars of two types, either regular lamp configurations or with these contour lights added. And, well, I call them contour lamps. As far as I know, the terminology is not fixed yet also in the industry, so other people may call them differently. But so these stimuli are based on 3D renderings. However, afterwards they were dumbed down to allow us to have a high degree of low-level control. So the psychophysical properties of these stimuli are very similar with the exception of the contour lamps added. So note also that the headlamps are the same also on the motorbike and on the cars. And so participants were first shown these three images one by one so that the experimenter could make sure that everyone could see the details of the stimuli and the silhouettes against the slightly brighter background clearly. And then they completed a training block with 9 trials, 6 signal and 3 noise trials. So signal trials are when the motorbike is actually present, and noise trials where there is no motorbike. And so participants have to respond accordingly in signal trials with one button. In noise trials, when they have made sure that there is no motorbike in the whole scene, then they would press a different button. And after practicing in this training block, they completed 4 test blocks with 30 trials each, with the 2 conditions blocked. And so this is kind of how the scenes look like. These are 2 scenes. The left side is the regular headlamp configuration, the right side is the contour lamp configuration. And of course it's kind of hard to illustrate here because in the lab there was the surroundings were dark, and so the relative contrast, particularly that between the main headlamps and the rest of the scene, were much larger. One participant described this as like when looking into the rear view mirror on the highway. And so you can see both of these are signal trials. So here's a motorbike and here's another one. And the flow of the experiment was the usual. So participants were fixating on a central fixation cross for an intertrial interval of 1 to 1.5 seconds, after which they were presented with a scene like this with random object locations, always different, of course. And then they had to find the motorbike. When they found it, they had to fixate on it and press a button. When they were sure that it was not there, they pressed a different button. And the instructions emphasized that they should be more accurate than quick in their responses. And after testing 22 participants for 120 trials each, this is what we found. Basically, in all measures that we had, we found a significant improvement in performance in the contour lamp condition relative to the regular headlamps condition. Our main measure was D prime, or discriminability, which is calculated here the usual way, so the difference between z-scores for hits and false alarms, and that gives us a number which shows discriminability. So in another word, it also means, or another way to look at it, is that the participant is more sensitive to perceiving the target correctly when this number is higher. And our second measure is reaction time. Again, participants were instructed not to hurry too much. Nevertheless, we see an improvement in this, again, showing the advantage of the contour lamp condition. And seeing this together with our first measure is interesting because that shows us that the advantage is not just due to some kind of trade-off between speed and accuracy, but rather it was a real improvement or real perceptual ease relative to the regular headlamps condition, because both of these measures showed an improvement. And then based on eye data, we further divided reaction times into saccade latency. That is the time that it takes for participants from stimulus onset until the first saccade away from the central fixation location. And this is interesting because it shows a quick first grasp of the whole scene, again tying it back to peripheral perception and crowding. So the target of the first saccade can only be planned based on peripheral perception here. So the shorter this time, the quicker the initial overall grasp of the scene was. So we saw a significant reduction in this time duration. And then the second phase is the actual searching, called scan time. So the time from this first saccade until the first fixation onto the target. Similarly, we see an improvement here. And then the third phase is called verification time, which is the time it takes the participant from the first fixation on the target until decision was made. So if this time is shorter, as it is for the contour lamps condition relative to the regular headlamps condition, that means that the identity of the target was clearer, or the decision was clearer quicker. And then lastly, we had a measure called the scan path ratio, which is the total distance that the eyes traveled before they found the target, divided by the shortest distance from the central fixation to the target. And again, here a shorter path, or a smaller scan path ratio, would show relative perceptual ease. And so all of these measures show an advantage of these contour lamps in this paradigm, which is very simplistic. Intentionally, it uses schematic images. But now that we have this as a first step, as a first experiment, as a baseline, it would be very easy to similarly 3D render stimuli which are of higher fidelity, so more realistic. And for instance, in this paradigm or other paradigms of classical cognitive psychology, we could compare two novel lamp layouts against each other, which one is better in terms of crowding. And such paradigms also offer a level of control that we cannot have in real-life paradigms, which are often used for studying perceptual aspects of light fixtures, or in simulator studies, which usually, if they focus on high-level perception, they would be usually more about situation awareness and driver reactions and stuff like that. So I see a relative lack of similar studies. It would be very useful to see more data along these lines, particularly because with the improvement in technology, lamps are becoming more complex, and high-level perception is becoming relatively more important. Or conversely, we could use our knowledge of high-level perception to develop better products and eventually to decrease glare. So glare is a big issue. It's continuously increasing on the roads. And if our knowledge of high and low-level perception together would be taken into account and integrated as well, which would require more such studies, I would say, and an approach which at least looks at these studies, then we would see implementations of low color temperature, of large luminous surfaces with low luminance, of patterns of these extended daytime running lights or contour lamps, or also current daytime running lamps, which do not elicit pattern glare. And of course, we should not see any flicker. And regarding all four of these aspects, that is definitely not what we see when it comes to current products as they are being developed. And so I would hope that others would join in doing such studies. And with that, I thank you for your attention, and please let me know what you think.